Okay, so hi everyone. Thank you for having me in this mini-symposium. So we'll talk about a method, parallel method for the advection of Schmidt scalars in flows. So first of all, I will. Okay, I will give an introduction of what is the hybrid method, which is a remesh particle method. I will tell you how we validated it, and then our numerical implementation, and then I'll show some numerical application about with this method, which is the advection of an Schmidt scalars in a turbulent jet. So, okay, the problematic here is very simple. We are going to deal with those two equations, the Navier-Stokes equation in its incompressible form, and the advection diffusion of a passive scalar, which is advected with the velocity, which is computed from the Navier-Stokes equation. So this passive scalar can be the temperature, the reacting species in a turbulent jet or whatever. And we will introduce the Schmidt number, SC, which is simply the ratio between the viscosity and the diffusivity coefficient of the passive scalar. So as you can see, the highest the Schmidt scalar is, the more you the passive scalar acts, diffuses less, and then acts as a level set. And then the second thing we are going to introduce is mu b, which is the Bachelor scale, and it is the smallest scale at which the scalars variates, and it is linked with the Kolmogorov scale, mu k, which is the lowest scale at which the velocity acts, and it is linked with the Bachelor scale with the ratio on the ratio with the square root of the Schmidt coefficient. Okay, so if you want to deal with this problem with classical method, you have finite volume method, finite element method, finite difference method. The problem is that every of these methods are subject to a stability condition, which links the space step of your grid and the time step of your K. So I give here the example for the 1D convection, and so this problematic is then linked with subject to two constraints. A physical constraint, the Kolmogorov-Bachelor condition, and a CFL condition, which is a numerical constraint. So what does it imply when the Schmidt number is very high compared to 1? If you want to treat this problem in a monolithic way, if you use a mesh which is adapted to the velocity, you have an accuracy on the velocity which is okay. The time will be let's say a cup of coffee unit tea. On the contrary, for the scalar, the accuracy will be very bad due to the Kolmogorov-Bachelor condition, and the time will be the same computation. On the contrary, if you use a mesh adapted to the scalar, the accuracy on your velocity will be, you will be over accurate for the velocity, and the time of your computation can be extremely long. And the accuracy on the scalar will be okay because you use a mesh which is fine enough to capture every variation of the scalar. And the time, due to the CFL condition, can be very low. So the wide range of scales for this phenomenon leads naturally to the use of two meshes, which is that's why I'm going to introduce the hybrid method I was talking about. The Navier-Stokes equation are solved on an unstructured mesh, thanks to a classical numerical scheme. In our case, it will be the finite element method. And the advection diffusion equation is solved on a Cartesian mesh, thanks to the remesh particle method. And those two meshes are superimposed. So how the remesh particle particle remesh particle method works. So as I said before, a Cartesian mesh is superimposed on the velocity mesh. At each node of the Cartesian mesh, there is a fictional particle which holds the value of your scalar function at the position x at the time t. Those fictional particles are advected thanks to the velocity fields, which were previously computed with the Navier-Stokes equation. And then after the advection, the weight of each particle is then redistributed on each point of the Cartesian mesh, thanks to this complicated formula. This complicated formula, this formula is not very interesting. It's not interesting to remember it. The thing is that this remeshing kernel has compact support, so then you can, numerically speaking, you can parallelize your method. And this method is also subject to a stability condition, but this stability condition does not include absolutely at all the space step of your grid. So this stability condition is far less restrictive than the CFL condition from the classical method. So as a scheme is better than 1,000 words, as I said before, you have a fictional particle which holds the value of your scalar. It is advected, and then the remeshing kernel redistribute the value on the point around the arrival point, arrival position of your particle, and then at the next time step you have a new scalar field. So how we validated this method? We use the case of turbulent, homogeneous, isotrope turbulent, and we consider. So this is the basic initial condition of the test case, and then we are going to study the evolution, in fact, the derivative of the evolution of the root mean square of phi, and for different Schmidt number. And we are going to compare with, in our case, a pure finite volume method. So in that case, on the left, you have the derivative of the evolution for a pure finite element method, and this is for a Schmidt number which is lower than 1. So normally, the pure finite volume method will have correct results, and this is completely the case. There is a reference solution. Oops, sorry. What happened? Okay, there is a reference solution which we even can see because we are already converged. On the left, this is for pure finite element method, and on the right, this is for our remesh particle method. And this is for 3 grid size, which goes from red, orange, and green. And for a Schmidt number, which is in this case equal to 6, the pure finite volume method has difficulties to converge. On the contrary, for our method, rematch particle method, we are almost already converged with the lowest resolution of the grid size. Okay, so how we implemented it? So, as it is a multiphysics problem, a classical way to deal with those problems is to use separate resources. One to solve Navier-Stokes equation, and on the other side, another group of processors are going to deal with the advection diffusion equation. So basically, the workflow of our coupling algorithm is it works in a serial fashion. So once you solve, whoops, what happened? sorry. You solve Navier-Stokes equation, then you send and receive the velocity field to the processor which are dealing with the advection equation, and then you solve the advection diffusion equation, etc., etc. The problem is that, of course, it leads to a lot of idle time, as when Navier-Stokes equation are being solved, the processor who are dealing with the advection diffusion equation are not working. So the first idea to solve this problem, which as there is a lot of idle time, is to overload the core so that every core involved in the computation works every time. The problem is of that overloading process is that a lot of CPU cycles are used just when you are waiting for a message, in this case, sending or receiving the velocity field, or at the end of the advection diffusion equation, there is a delta T synchronization, and with it's also a moment when a lot of processors have to wait. So this problem, as I said, it leads to worst computational time. So we are going to overload the core, but we use also an external library, which is called the DLB library. And this library allows us to remove the CPU cycles while waiting for a computation. And so finally, the new workflow of the coupling algorithm is the most simplest, in fact. You solve Navier-Stokes, then you solve the advection diffusion, and you have absolutely no idle time, as every CPU involved in the computation works every time and doesn't use CPU cycles while waiting for a computation. Okay, so I give here. Okay, I give here the two different traces for the two cases. One on the left without the overloading strategy. So as you can see, you solve Navier-Stokes on the gray, then all the green time is the time spent in the waiting for a message in the coupling subroutine or the coupling function. Then you solve the advection diffusion equation, etc., etc. And when you use our strategy of overloading, it leads to a speed up almost equal to 2, and the time you spent in the coupling communication is then completely negligible right now. Okay, so I will give you some images to characterize an Schmidt scalar in a turbulent jet. So I give you some numerical statistics. So it's a basic turbulence jet. The Reynolds number is equal to 2000. The mesh read is composed of 60 million. We have 1 billion particles, 200 procs, etc., etc. But just numerical statistics to give you the load of the computation. And then, so this is some snapshots of our scalar in our turbulent flow for a Schmidt number equal to 1, equal to 10, and then equal to 20. So as we can see, the highest the Schmidt number is, the highest the sharpness of the gradient, the sharpness of the variation R. We can see that the gradient is sharpest in the small structure of the flow. So you can also see in that in those picture the mushroom shape, which is a classical, which is the signature move of the ejection of current vortex out of the jet. And in the small structure, especially in the center here, the gradient is a little bit more intense in the small structure of the jet. As expected, the means are completely the same. Concerning the root mean square, as expected, there are more turbulence. The turbulence field of a scalar is a little bit higher in the turbulent non-turbulent interface, and the highest the Schmidt number is, the highest the turbulent field is high. The highest the turbulent field is, sorry. This is the profile along a diameter for different Exxon error value, for 2 here, 7 here, 10 here. This is a quite a bit difficult to see the different values between 1, 10, and 20. But as expected, in 20, in the core of the jet, the gradients are very high, or the highest. Yeah. And finally, my last images will be it's the spectrum of a time series in the far flow, and so we can see the signature -5/3 slope of our scalar for different Schmidt numbers. So this was my last images. Thank you for listening to me.